Hey everybody, today we're going to talk about how to identify the waves of an EKG with Python. It may seem like a heartbeat is just a big spike and then a bunch of squiggly noise in between, but actually all of the bumps in between the big spikes correspond with a particular part of the heart squeezing, and the timing and the strength of each squeeze is very important. What we're going to do is take some real EKG data from a real person and feed it into a Python library called NeuroKit. And the NeuroKit's going to automatically find all of the waves for us. There are other ways to do this, such as using SciPy, a digital signal processing library, to build the algorithm yourself, but we'll go over this in a future video. For now, we're going to do it the easy way and just use a couple of functions from NeuroKit. NeuroKit will allow you to write maybe 1 or 2 lines of Python and process an entire EKG in one go. NeuroKit will find the P waves, the Q waves, the R waves, everything. It will even smooth the EKG for us and get rid of the noise and calculate the heart rate. But at the end of this video, you'll know 2 or 3 new methods for identifying all of these waves with NeuroKit. This video is going to be as beginner-friendly as I can make it. We're going to skip a couple of the introductory things that we touched on in the smoothing and graphing EKG videos. If you're 100% new to Python, I would recommend checking those videos out first. So overall today, we're going to show you how to get some real EKG data, show you how to install NeuroKit, and then show you 3 different functions that NeuroKit provides to find waves. And throughout the video, we'll touch a bit on what all of the waves mean and what part of the heartbeat they correspond with. Alright, this is the part that we're going to skim past a little bit because we covered it in the earlier 2 videos on smoothing and graphing. We're going to write and run all of our code on a free website called Kaggle. Kaggle has thousands of free datasets, and you can create a notebook to run code on them and analyze them. You can even run code in Python or R. We've uploaded a free dataset to Kaggle of normal, healthy heartbeats. This dataset was collected by a team at MIT and some doctors at Beth Israel in Boston. There are 18 EKGs from 18 real people, and they're all about 24 hours long. But we only need 1 EKG from 1 person for just a couple seconds to show you how NeuroKit does the wave finding. The link to this dataset is going to be in the description, so go over to this dataset on Kaggle, make sure you create a free account, and then what we'll do is go to, in the top right, the 3 dots, or the options, and create a new notebook. And then this dataset will be automatically included into our Python code. All we'll have to do is write 1 or 2 lines to open the files themselves, but then we'll be able to immediately start analyzing real EKG data. Once we open our EKG data, it's going to kind of look like this. Remember, each spike is 1 heartbeat. Alright, let's name our notebook. I'll name it YT for YouTube. Label EKGs with Python and NeuroKit. And by labeling, I mean finding all of these actual waves. Alright, let's get rid of this placeholder code, or most of it. We only need Pandas. Okay. So as a reminder from our last videos, we use Pandas to open the CSV files of EKG data. Over here on the right, you see all of the CSVs included with this dataset. Not only are there files with real EKGs, but there are annotation files where doctors have actually come in and manually labeled each heartbeat and said this is a healthy heartbeat or this is an unhealthy heartbeat. And what kind of unhealthy heartbeat is it? For example, atrial fibrillation, ventricular tachycardia, all names of arrhythmias that we'll go over later in this series. Alright, so the libraries that we're going to need are going to be Pandas for opening the EKG data. We also need the graphing library, matplotlib.pyplot. And then we're going to also use NeuroKit. The actual name for NeuroKit, when you write it in Python, is going to be NeuroKit 2. Now, thanks to Kaggle, because it's so data science friendly, it already comes with Pandas and Matplotlib. They're already installed, and then we just have to import them. However, NeuroKit does not, so we have to install NeuroKit first. What we're going to do is make a new code block, click and drag it to above the import cell of code. We're going to use the Python package manager called pip, P-I-P, to install NeuroKit. What we're going to write is pip pip install NeuroKit 2, and we could technically install it just like this and run this block of code, but we're going to add --quiet so that a bunch of crap doesn't just get printed into our notebook. So let's run that. You can either click the run triangle button or press shift return or shift enter to run that cell of code. Now our Kaggle notebook is starting up. This will take a minute or two. Alright, NeuroKit is installed. Now we can import everything. We're going to run this cell of code. Let me add some titles to these sections. I'm going to add some markdown that says install and import libraries. Press shift return, and that just runs the markdown, so to speak. But again, it's just a comment, so it doesn't actually do anything. Okay, pip installed NeuroKit, imported everything. Alright, we'll make a new block of code. Alright, now we're going to open the EKG data with Pandas. Pandas has a function called readCSV. All we have to do is give the file name to readCSV, and it'll open our EKG into a Pandas data frame. As a reminder, a data frame is like a rows and columns based piece of data. Think of it like a super simple spreadsheet. Alright, so our file path, let's go over to the right. We're going to copy our file path by hovering over the name of the file that we want. Copy. We're going to store it in a variable called file path. Going to add some double quotes and then paste the whole file name. Folder slash blah 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 slash 16265 ekg.csv. And then we're going to give that to the readCSV function. And then we want to save the output of readCSV, so let's save that as ekg underscore df, df meaning data frame, equals. So the full line at the bottom is ekg underscore df equals pd.readCSV file path in parentheses. Alright, let's run that. It will open our EKG. And if you watched our previous videos on smoothing and graphing EKGs, you'll remember these files are 24 hours long, if not more, which means they're 500 megabytes, which means they take a while to open. Alright, let's look at what we have. Our data frame is 11.7 million rows long and 25 hours and 27 minutes of EKG voltage data. So for columns, we have the timestamps of each of the voltages, and we have the voltages themselves. Like every EKG in this data set, the team at MIT that collected this data chose to only include 2 out of the 12 possible channels from the EKGs in this data set. If you've ever done an EKG on a smartwatch, it only records 1 lead. However, when you go to a doctor or go to the ER or somebody calls the paramedics, they're going to do either a 4-lead or a 12-lead EKG. What you're looking at right now is a 12-lead EKG. This looks at the heart from 12 different angles. This is so that doctors can pinpoint if something's going wrong, exactly where it is going wrong. Is it on the left side of the heart, the right side, the bottom, the top? The right side of a person's heart could look totally fine electrically, but maybe the left side is having some issues. So the shape of the recordings for whichever side of the heart is having trouble is going to change. So for all of the MIT BIH EKG datasets, of which there are dozens, they have included 2 channels for each patient in every file. It seems like they just chose whichever channels they thought were most relevant. For the normal sinus rhythm folks, for the first channel they basically chose either lead 1 or lead 2, and then the second one was usually like lead 4 or lead 5, or AVL or AVF. Alright, let's graph channel 1 to get a better idea of what we're looking at. Okay, voltage channel 1. So to get channel 1, I'm going to do channel 1 equals EKG DF, and the column name is, with underscores, voltage channel 1 MV. Again, MV is for millivolts, because EKGs are very electrically quiet. We'll print out what we're looking at. Again, 11.7 million rows of EKG data. To graph, all we need to do is channel1.plot. This is going to show us all 25 hours. It's going to be a big blue blob. There it is. Alright, let's reduce this data. Again, we learned from the graphing video that this data was taken at a sample rate of 128 hertz per second, which you can see in the metadata file, metadata.json. So to get the first few seconds of data, we can get just the first 600 data points or so. We'll rerun that, and then we will replot it. And we have 8 heartbeats. Actually, this heartbeat is chopped off at the end, so let's get the last couple of data points. We'll do Data points 0 to 650. Rerun that, rerun the plot function. All right, 8 full heartbeats. Okay, so since we have 650 data points, divide that by 128 samples per second. That means we have 5.07 seconds of data and 8 heartbeats. All right, let's run this through NeuroKit and start finding actual waves. We're going to do this in 3 different ways. First, we'll use NeuroKit's ECG process function, which both smooths the EKG and finds all of the waves, and then we'll manually graph it ourselves with Matplotlib. The second peak finding method is going to be ECG delineate, which will automatically find the waves and graph them in a stacked fashion. These light gray lines are all of the heartbeats stacked on top of each other. And then finally, we're going to show you NeuroKit's ECG find peaks function. This one only finds R waves, but it provides about 20 different methods for doing so, all based on real research that has been published since the 80s. Using ECG process is going to be pretty simple. The bulk of what we need to write is going to be neurokit2.ecg process. And then the arguments that we're going to give to the function are just going to be the EKG and the sampling rate. Remember, that's 128 hertz. So let's delete that. Okay, so we're going to let's assign the output of this to a variable called processed EKG. So we have processed EKG equals neurokit2.ecg process. And then we're going to give it the EKG, just those 750 data points that we got earlier. So we'll give it channel 1 and the sampling rate, sampling_rate equals 128. Let's run that. And our EKG is processed. Let's print out what we got. All right, so we're going to see 2 things. The first, these rows and columns, is actually a data frame of the processed EKG. And the second is a bunch of metadata with the locations of all of the waves it found, the R waves, the P waves, the Q waves. So if we want to get just the data frame, we could say processed EKG brackets 0. Let's print that, see what we got. Here's the data frame. We have the raw EKG data in column 1. We have the cleaned or smoothed EKG data in column 2. We also have the heart rate and all of the peaks in the columns to the right. But we won't use these columns to graph. We're going to use that metadata dictionary that was in the second item. We're going to use these ECG R peaks and ECG P peaks, ECG Q peaks. Let's look at the data frame again. Let's move this data frame into its own variable. So we'll call it processed_EKG_DF equals item 0 of the processed EKG. And now processed EKG is its own data frame. We'll print that. Okay. And then we'll say metadata. We'll pluck out the metadata from the processed EKG. Say metadata equals processed EKG item 1, which is the second item of the tuple. Let's rerun that and make sure our metadata is what we expect it to be. Run that cell of code with Shift-Enter. There's our metadata. All right, let's graph this. So we're going to graph this in layers. First, we'll plot the regular EKG itself, and then we'll create a scatter plot on top of that with the indexes of the peaks that NeuroKit found. So we're going to graph actually the smoothed EKG. Remember, we have the raw EKG in one column and the cleaned or smoothed EKG in another. So we'll do processed EKG DF. The smoothed EKG is in the column ECG_clean, and then we just run .plot on that. And there are 8 heartbeats. You can see that the EKG is a little smoothed out. Not completely, that's not what we want. We do want some of these blips and boops because those are the P and T waves, and we definitely want to keep the R waves. But it's better than the super jagged, unreadable version from before. And if you want to get deeper into the smoothing algorithms, please check out our How to Smooth an EKG video, also available on YouTube. So there is our smoothed EKG. And then to plot the markers for the waves, we'll use a scatter plot, which we can call with plt.scatter. we actually have to do this separately for each type of wave, separately for the P waves, the Q waves, the R waves, etc. So we'll have 5 separate parts where we're calling plt.scatter. Let's show you how we do it with the R waves. So for our scatter plot, we're going to need to give it an X and a Y. Our X is going to be the R waves. So we'll say from our metadata variable that has this dictionary in it, metadata, it was called ECG R peaks. So we'll say ECG underscore R underscore peaks. That's capitalized. Peaks. And then the Y is going to be but at the index of X. By doing this with Y, it will match the exact height of the R waves. If we just gave it an array of like 8 ones, it would just plot the dots at 1, at Y equals 1. But if we give it this, and then say, hey, from this clean EKG, only get the items. This is kind of like doing, 0 to 100, but it's saying I just want it at the indices that X holds. Then it will plot the exact heights of the R waves. Just so you can see what Y is. Let's run that. It's the exact voltage values at the indexes where an R wave is occurring. Index 54, index 131, etc. Alright, let's change the color of this just so the R waves stand out. We'll make this color equals red. And those are the R waves. Alright, let's do this for all of the other waves. The P, Q, S, and T waves. So we're just going to copy and paste this. I'm going to say add the R waves. Add the wave markers for R waves, and then we'll copy and paste. Alright, copy. Let's put these in order, because it's PQRST. So we'll say, alright, this first one will be the Q wave, the P waves. Add wave markers for P waves. We'll change the column name to P. We'll make this green. Color equals green in single quotes. The next one we'll change to the Q waves. We'll make this color orange. And then we'll do the S and T waves. So we'll paste that. S waves. Let's make the S waves black. And then the T waves, we'll make them purple. Alright, let's run that. Alright, the waves have been identified for all of our heartbeats. Let's zoom in on a few. Looking at the first one here on the left, the R wave, of course, that's marked red at the top. The green one is a P wave. The algorithm didn't do that great at identifying the Q wave. It put the Q wave up here. It might be that it shifted the index of the actual Q wave to the data point to the immediate right of the actual Q wave. So maybe if the index of this yellow one was set to -1 of its current value, it might actually dip down to the bottom here. It looks like the Q waves are a little off on every one of these. We'll go over how to fix that in a second. But we have the green are the P waves on the left, yellow are the Q waves, red are the R waves. The dip to the right of the R wave is the S wave, those are the black dots. And then the T waves are the purple dots. Remember that when you're looking at a heartbeat, the main things going on are you have the big R wave spike in the middle. On the left and the right are little bumps, the P and T waves. And then the dips immediately next to the R waves are the Q and S waves. So it's a little bump, then a big spike, then a little to medium bump after. There's also something known as a U wave that could appear over here to the right of the T wave, but we'll cover that in a future video. Alright, let's try to fix those Q waves. Let's see what we can do. If we just take X, and what if we subtract 1 from it? Will that shift everything over how we want it to? Since X is a list, we're going to do something called list comprehension to subtract 1 from every item in X. So we're going to say we want everything in it to equal item -1 for every item that exists in X. Let's run that and see how it does. Yeah, okay, that fixed it. All of the Q waves look like they're in the right spot at the very bottom of the wave. If you want to learn more about what I just did, this is called Python list comprehension. You can write a for loop in one line, which makes it easier to change lists. Alright, our Q waves are fixed. Let's delete that. Alright, that was the first method for finding waves with NeuroKit using ECG process. Now we're going to use a function called ECG delineate. This is going to get us results that look like this, where all of the heartbeats are stacked. One thing you need to do before using ECG delineate is to smooth the EKG. We showed you a few methods in the How to Smooth an EKG video, also on YouTube. To speed things up, we're just going to use the smoothed EKG that we just got from the ECG process function. Remember that that was in the column of the processed EKG data frame. The column's name was ECG_clean. So let's just grab that and assign it to its own variable, smoothed_EKG. And we'll have 650 voltage values of the smoothed EKG. So to run ECG delineate, we have to give it 5 arguments. That's going to be first, the smoothed EKG. Second, the locations of the R peaks. However, this is optional. It will still be able to create this graph if we don't give it the R peaks, it just won't mark them. We'll give it our sampling rate for the data, 128 Hertz. And then there's an argument about whether we want to see a graph afterward or not, called show. So we'll set the show argument to true. And then the last argument is the method we want it to use. ECG delineate provides 4 different methods: peaks, continuous wavelet transform, discrete wavelet transform, and prominence-based peak finding. We're going to use a simple one, peaks, for now. So when we give the argument, it will be method equals peaks, in quotes. Alright, let's feed this information into the ECG delineate function. So we're going to write, we don't need to assign this to a variable. Because all we want is a graph, we can run the function by itself and it will just create a graph. So we're going to write NeuroKit2 dot ECG_delineate. First argument, the smoothed EKG. Next argument, let's give it the R peaks that we found in the previous function. Again, that's held in the metadata variable, metadata ECG R peaks. Let's copy that. So we're going to say R peaks equals metadata brackets and in quotes ECG R peaks. So that will be our second argument, and we have to be explicit for this function and tell it that the R peaks argument is going to equal R_peaks. Our sampling rate, again, we have to be explicit with this argument, is going to be 128 Hertz. So we just write sampling_rate equals 128. Alright, our next argument, we'll put it on the next line to make it readable. We'll say show equals true. This tells it that we want to see a graph once this function runs. And in the method, we'll write method equals peaks. If we wanted to use the other methods, we could say for continuous wavelet transform, we could write method equals CWT. For discrete wavelets, we could write DWT. And then for the prominence method, we would just have to write prominence. But for now, we'll run it with the peaks method. What it's going to do is print a bunch of stuff, but the graph is going to be at the bottom. There are some improvements that could be made. The algorithm is not perfect. It's harder for computers to find waves on some people's EKGs than others. Let's show you one where it does work. We're going to run this whole notebook with a different person's EKG and show you what happens when there are EKG differences between patients. So let's go all the way back up to the top where we chose our EKG file. We're going to choose an entirely different person. So here we have file path where we're opening the CSV. Let's change this to patient 16272. You can see their EKG is listed over here on the right. So let's rerun everything with this person. I'm going to click run all, and it will run everything from top to bottom with this new person's data. Alright, their data is loaded, looks almost the same. Alright, their peak finding graph from the first method already looks better. And the second method, ECG delineate, did even better on this EKG than the last patient's. Let's try another patient and see how it identifies their EKG waves. Let's rerun this notebook on patient 420. Come up here and click Run All to rerun the entire notebook, and we'll see how it did on this person. All of these EKGs are again supposedly from healthy people, so the NeuroKit algorithm shouldn't have trouble identifying waves in everybody, but again, not every algorithm is perfect. That's why the NeuroKit functions have so many methods that you can choose from. Some methods fail more often than others. Some are good on only healthy heartbeats. Some are better at finding peaks when the EKG is super messed up and the person has an arrhythmia. Alright, here's their EKG after ECG process. And ECG delineate did an okay job. It accidentally tacked on the P peaks from the next heartbeats onto the main graph, so we're just seeing the P peaks twice on the left and the right. So again, what are we looking at when we're seeing these waves? We're going to go back to the second patient's EKG since theirs looked the best. Patient 16272. Going to rerun the whole notebook. So each of these blips, each of these big spikes is the R wave from the heartbeat. Again, you have a little bump, a big spike, and then a medium bump after. That's pretty much what an EKG looks like. If we zoom in on one, we have a green dot, that's the P wave. Red dot is the R wave, that's the big spike, and the purple dot on the right is the T wave. The reason that we care about finding and labeling these is because each blip is a step in the heartbeat. As you see in this animation of the heart, there's like a cadence, like da-da, da-da, lub-dub, lub-dub, and you can think of that as corresponding with the P and R waves. Instead of da-da, da-da, think PR, PR. Atria ventricles, atria ventricles. So the timing of all of this is very important. Even this little pause between the P wave and the R wave, if that is too short or too long, that's not healthy. During a heartbeat, what the atria are doing is just accepting blood coming back from the rest of the body or the lungs, and then all they have to do is move it down to the ventricles. It's the ventricles that squeeze everything out to the rest of the body. So the reason why these little in-between parts matter, the PR segment and the ST segment, is because pumps need accurate timing. If the PR segment was too short, if the P wave and the R wave were right next to each other, the ventricles actually wouldn't have time to fill with blood, and then they wouldn't have anything to squeeze out to the rest of the body. So when doctors are looking at all of these segments and intervals and making sure they're not too long or too short, they're making sure the pump that is the heart is filling with the right amount of blood and pumping it at the right time. There are heart diseases where certain parts of the heart are filling with too much blood or not enough blood, and this can lead to issues in the rest of the body. Swollen ankles, kidney problems. I'm not a doctor, so I can't diagnose you. Just know that there are a dozen steps that need to be timed just right. There's a little bit of wiggle room in how long or short each part of the EKG is supposed to be. For example, the PR interval is supposed to be 120 to 200 milliseconds. You can come to this website, Life in the Fast Lane, to learn more about what those values are supposed to be. This site is used by doctors, nurses, and paramedics who work in emergency medicine to better understand how to read EKGs. To review before we move on to the last peak finding method, here's what we're looking at. The blue dots, those are the atria contracting, and then there's a pause before the big spike R wave. The orange dots are also the Q waves that NeuroKit found. Then the big spike R wave is the ventricles contracting and squeezing blood either to the lungs or to the rest of the body. The green dots are the S waves. The S waves are actually the end of the ventricular contraction. And then the red dots are the T wave. The T waves are the electrical reset of the ventricles. And the cells have to reset so that they can prepare for the next heartbeat. If the cells don't reset properly, then the next heartbeat may not happen properly. Alright, for the last method, we're going to use a simpler NeuroKit function called ECG find peaks. This one only finds R waves, but you can use it as input into bigger NeuroKit functions like ECG delineate. To use this one, the bulk of what we have to write is neurokit2.ecg underscore find peaks. And we'll give it 3 arguments, nothing you haven't seen before. First is our smoothed EKG. Second is the sampling rate, which you've already seen, 128 Hertz. And then our method, we'll use the default method, which is just NeuroKit. And then we'll save that in a variable called rwaves. So it's rwaves equals NeuroKit2 ECG find peaks with the 3 arguments: the EKG, the sampling rate, and the method. Let's run that. Let's print out our rwaves, r_waves, shift return. We have a dictionary with an array of the indices of the rwaves it found. Let's extract the actual list or array from the dictionary. So we'll just say rwaves equals ECG_r peaks. And now we don't have the dictionary with the label, we just have the values themselves. And let's graph this. So like we did in the last steps, we're just going to graph the EKG by itself, and then we'll use a scatter plot to graph the dots for the labeled rwaves. Alright, so we'll do smoothed EKG dot plot. There's our EKG. And then for the rwaves, we'll say, kind of like before, we'll separate out x and y. X equals the rwaves, this array up here, and then y equals the smoothed EKG only at the indices of x. And then we'll create the scatter plot with plt.scatter parentheses x and y, and we'll make the color of the dots equal to red. And there are our rwaves. And that's everything. Let's review what we did. First, we installed NeuroKit 2 because it does not come built into the Kaggle notebook. And then we imported NeuroKit 2, imported Pandas and Matplotlib for opening CSV files and graphing. We used Pandas to open the file. We graphed just the first 650 data points or voltages from channel 1 of the EKG. Let's change this title. That's actually 5 since we changed patients. First 5 heartbeats. Then we ran our EKG through ECG process. Got a clean and smooth EKG with all of the peaks identified. Then we graphed it. Then we tried a totally different NeuroKit method, ECG delineate, where it identified all of the peaks and graphed them in a stacked fashion. And then lastly, we used the super simple ECG find peaks function to find just the rwaves, and then we graphed those. For each of these functions, again, there are a few methods you can choose from that NeuroKit provides, and you can read more about these in the NeuroKit documentation, as well as the actual code itself. They have comments in the code that tell you which methods the functions accept. So here we have NeuroKit. We have a method from a paper from 2002 by Hamilton et al., and so on. That's it for today. Thanks for watching. If you have any questions, please leave them in the comments. If you have any feedback about how I can improve, let me know in the comments also.